Have you ever been sad because all the names you know are boring and you are holding an unnamed newborn child? Well, be sad no longer because we are about to teach you how to make your very own name generator using neural nets, backpropagation, and gradient descent. The first step to understanding this whole name generator business is to understand gradient descent. Gradient descent is the process of finding a local minimum of a function by iteratively changing a location in the opposite direction of the gradient. This can be expressed by xn plus 1 equals xn plus the learning rate times the gradient of f of x. That's a bit abstract, so let's see what this looks like. Here's the function f of x equals x to the fourth minus x squared. Let's say we wanted to find the minimum of this function computationally, and not analytically by finding the part where the derivative is 0 and the second derivative is positive. We could start at a random point like the green dot in the top right and take the gradient at that point and then move in the opposite direction. For example, the gradient at x equals 1 is 2. 2 is a large step to take, which is why the gradient is multiplied by a learning rate. For the sake of this example, let's say that the learning rate is 0.05. Our new position would be 0.9. If we perform this enough times, we'll end up with a path like the one on the graph. A local minimum appears on the graph whenever the gradient is equal to 0. Notice how there are two local minima, so depending on where we start, we could end up in either of them. Gradient descent works great when you start with a function already defined, but when working with a set of data points instead of a function, gradient descent is not appropriate. With complex systems like a neural net involved in our name generator, we need to introduce equations to find minimums. The solution? The cost function. There are many, but a common one is simply c of h and y equals 1/2 the sum of y minus h squared. In this graph, y is the line of best fit for the observed results, and h is a random prediction. You can see the h value at position 1 has a higher error than the h value at position 2. Summing up the errors for each point on h equates to the cost value for that prediction. With this definition, a low-cost function would describe a model in which the predicted outcomes closely match the observed outcomes, while a high-cost function would indicate a large discrepancy between the predicted and the observed. If h is plotted against its respective cost value, the resulting graph is a parabola. This is because the error is squared. The smaller the error, the better. So the minimum of the parabola is the most accurate prediction. We now have a function that approximates how good our model is. Linear approximations are nice, but they are very limited in what they can predict. A nonlinear function is required. However, when picking a nonlinear function, it is very important to consider the outputs it generates because it is an iterative process, and future outputs depend on past outputs. Therefore, we would probably want a probability between 0 and 1 to prevent any ridiculous numbers and ridiculous calculations from occurring. Well, there's a very nice function for that, the sigmoid function. The sigmoid function is f of x equals 1 over 1 plus e to the negative x. Just like we wanted, the sigmoid function takes any input of x and computes the output between 0 and 1. We can even plug in the cost function as the x value so that the output of the sigmoid function is dependent on weight and bias. And from here we can rewrite our cost function, where the observed value y is either 0 or 1 to denote whether the input is part of the class or not. In our case, it represents which letter node is triggered, where the value 1 indicates that the letter is triggered and 0 means it is not. Now that we have defined the math, we can build a neural net. The diagram on the left is the graphical representation of y equals w times x plus b that we saw before, where b is the bias, w is the weight, x is the input, and y is the output. If we add more inputs and outputs to the model, it will look like the diagram on the right. This is cool, but it only has an input and an output. If we want to add more complexity to the model, we can repeat this structure to add layers. Notice that the hidden layers acts both as an input for the next layer and as an output for the previous, meaning it has both weights leading forward and an error associated with it. There could be an arbitrary number of these layers, and you can get these derivatives for all their weights by calculating the error of one layer given the error for the next layer and the weights connecting to it. This is a process known as backpropagation. For more information, check out the paper in the description. In this structure, we have a node representing each possible letter in each of the 3 previous letter spaces. This connects to a hidden layer of 39 nodes thick. The number in this layer is an arbitrary value. The hidden layer connects to an output layer of 26 nodes, each representing a different letter. The neural net is trained by going through every letter in a word from a database, starting at the first letter. Then we set the corresponding input index inside the neural net to a value of 1. So AAA would have a 1 at the 1st, 27th, and 53rd node. We then forward propagate to get the probability of the next letter being each letter in the alphabet and back propagate to compare the actual next letter is, adjusting our weights and biases accordingly. After running this for a while, say 40,000 times. We finally have our trained name generator. We then start to generate unique names through an iterative forward propagation, having the output of the net be part for the next input, and sample from the letter distribution according to the likelihood of each letter. So, if the net is 70% sure the next letter is an A and 30% B, we would then have a 70% likelihood of choosing A for our next letter versus B. Put all that snazzy math together and you got yourself a neural net capable of coming up with such unique, creative, and Pinterest-worthy names such as Diane with a Y and 2 N's.